All right, let's get started. So let's go over the exam. And then you can ask questions, whatever. Feel free to interrupt as we go. So this is exam number 2. Oh, I didn't turn on. Is it on now? Yeah. It's supposed to go automatically. Okay. Huh. Now we'll go back to. I don't know. I can't get the thing to go back to projector 1. There, got them both. Okay. So this is EET321 exam number 2. The first problem, you had a 3-phase 4160 or 4170 kV Y connected synchronous generator has XL equal to a value in RA and is operated to provide rated voltage at the terminals. So the first thing I do is I start to draw a diagram. Here's my. Yep.
Could you share the screen?
Oh, sorry about that.
Thank you.
Thought I was. So here's EA. Here is, and it doesn't really matter. We'll call this JXS. Here is RA. JXS was J2.2. And this is 0.15. And then the thing it said was it's operated to provide rated voltage at the terminals. This is a Y connected synchronous machine. So you have to take your voltage, which was 4170, and divide that by the square root of 3. And we set that as an angle of 0 to do our reference. We've done this a number of times in this class. Hopefully it's not too foreign of an idea. Now, this is where I would recommend you start and continue on, but a lot of people struggled as to the load calculating the current. So some of you all assumed that your current was calculated by putting a short circuit across the terminals. Because what you said was I is equal to 4170 at an angle of 0 divided by the square root of 3 divided by 0.15 plus J 2.2. Is that correct? That would be if you had a short circuit across the terminals, but more importantly, this voltage could not be 4170 divided by square root of 3, right? Around 2400. So you couldn't even get this to work if you did this equation. So that's why when I say, go ahead and draw your diagrams, you can actually see how things lay out. You pretty quickly would have determined, hey, the only way I can get this current like this is if that's a short circuit, which we know it can't be if the terminal voltage is 4170, right? A short circuit, the voltage is going to be 0 because there's no impedance. So this was the wrong approach. What you should have done is connected a load across here. And this load is 950 kVA at a 0.8 power factor, and it is lagging. So then to calculate I, S equals the square root of 3 or 3, depending on which one you do, VI conjugate. Okay, so this is line quantities, and these are phase quantities. If you use the 2400 volts or whatever the 4170 divided by square root of 3 is equal to, then those are phase quantities. You would use this equation over here. If you use the 4170, then you would use that equation over there, because in a Y connected circuit, I line and I phase are the same, right? In Y connected circuits. So we'll just pick this equation over here. So I line is going to be equal to S divided by square root of 3 V line, and we're going to take the conjugate of that. Now, there's a couple ways to do this one. I just, kind of write it out, but you have to remember this S has an angle associated with it. And to determine if it's a positive or negative, you need to recognize that the voltage is here. My current is lagging down over here. So when I do this as the power triangle, here's my P, my Q is here. So this angle is positive. I have a positive angle there. So my way to go ahead and calculate what S is just to put 950K. And the angle is the positive inverse cosine of 0.85. Then I divide that by the square root of 3 times 4170. And that's at an angle of 0, so it's the same thing as 4170. And that's how you calculate I line. And that was the first question I asked, which is the phase current. And the reason why I asked that first question is it should lead you, that's the step you had to do first to be able to calculate the internal voltage. So you calculate I first, and that was what required in the problem to kind of help get you started on the problem. What do you need to calculate first? It would have been a little sneaky to say, give me an EA before I phase, but I said, you know what, I'll just give them, a kind of approach to tackle the problem and then hopefully get them to feel more confident. Yes, ma'am. Mm-hmm.
How do you calculate EA?
Well, we'll do that for step B.
Oh.
This is part A. For part B, let's go back to this. I know the current here, I. We just calculated it. I know the voltage here, so now I can write a KVL equation. And we'll do the full Monty one. Negative EA plus I times JXS plus RA plus 4170 over the square root of 3 at an angle of 0 equal 0. It's just a KVL loop, right? When I'm in AC circuits, it's just a KVL loop. I didn't put the minuses and the pluses here, but hopefully you all can do those pretty quickly yourself and identify the pluses and minuses. So all you needed to do for part B, EA 4170 over the square root of 3 at an angle of 0 plus I times RA plus J XS. And that was it for problem 1 and A and B. Questions on that? Yes, sir.
For the XF, wouldn't that be the synchronous reactance? It says XL on the top, is that different?
Same thing, XL, XS. That would be the same value. So I will say, part A of the problem, that should have been, I'm not putting anybody down who didn't get it. That should have been 10 easy points. Because this is stuff we've been doing the entire semester. Do you recall at the beginning of the semester, it's like, this is going to be newer material and we're going to build and we're going to build. But this is exam 1 material. And if people are still struggling with how to do exam 1 material, it makes it very difficult to do exam 2 material, correct? So if you didn't know how to do part A, you might need to go back and look at some of that earlier material to be able to figure out what am I missing? What am I not understanding? Because all that is power triangles, right? Doing power triangles and S equals VI conjugate. There was nothing about whether this is a synchronous motor or generator, induction, it doesn't matter. This is just how do I calculate current given an S? So if you would have gone back to exam one, I could have said this same problem. I would have just taken out the synchronous generator. I said, a load is operated at 4170, and here's the load. Calculate the current to the load. It's the same problem for part A. Okay. Any questions or further discussion on A? All right, let's do our problem one. Let's go to problem two. So part A, you have a 25 horsepower sync motor. Doesn't matter if it's sync motor or generator, just know it's 25 horsepower. But normally, if it's rated in horsepower, that usually is indicative that it is a motor, because our mechanical engineering friends, at least in North America, like to work with horsepower and not watts. So we have a 25 horsepower motor. Its efficiency is equal to 92%. And its power factor is 0.8, leading. So how do you calculate the input power? What is Pin? Well, we got to solve for that, but we know efficiency by definition is P out over Pn. So Pn is just P out divided by efficiency. You should have calculated it to watts, mainly because input power, if we're trying to calculate currents and power and all that stuff, we would want to know what the input watts are. Because as an electrical engineer, we're way more interested in watts than horsepower. So we just do the conversion from watts to horsepower, 746. And then for part B, what is the kVA input? Well, power factor by definition is P over S. So S is equal to P over my power factor. This was exam one, this whole problem with exam one material. Nothing sneaky about it. But we can't just forget all the stuff that we use for our fundamentals. We have to keep building. So that's 30 points that should have been fairly, if you're at this point in the class, should have been fairly straightforward for you to get these points. That was my intention. Any questions on number two? All right, let's go to number three, which was, is that the hardest problem of the test? What was hard about it? First time you'd ever seen something like that? Maybe. Okay. Well, I gave you a tabular data, correct? So if you're not comfortable working with tables, draw a picture. So we have air gap line. We know it starts at 0. And then at 480 divided by the square root of 3, right? Because we're going to do things in single phase quantity. We have a field current of 14.7 amps. Okay. Then we have our open circuit characteristic, which says to get to that same value of voltage, I need 16 amps. So this is the V open circuit. This is the air gap. And then finally, I have my short circuit characteristic data, which says that, let's just go like this, because this is a different axis, right? This is my voltage axis. This is my current axis. So this says at 16 amps of current, I've got, let's see, I've got 452 amps. And at 21.3 amps, I've got 601 amps. So now it says calculate X sub U. Is there any curve on here that gives you the unsaturated reactance? Look at the air gap line versus the open circuit characteristic. Isn't the air gap line perfectly linear? What does the thing about saturation do? Start driving more current, it starts to peel off from the air gap line. Why? Because it is saturated. So your unsaturated reactance is that correct? A lot of people did this. Are you, a lot of you correct? No, because this is an AC voltage. What is this? A DC voltage. So what you needed to do is you needed to get the current at that spot here. I need to know, what is that current? Do you have a way of calculating that current? Don't you know that this is a linear line and this is a slope? You can get the slope of the line. So the change in Y, so M for the short circuit characteristic, the change in Y, whoops, is equal to 601 minus 4, oh boy, minus 4, really doesn't want to cooperate here, minus 452 over the change in X. What are my changes in X? What is the X-axis? Field current. So what number should I put in there? 21.3 minus 16. So this gives me the AC current change relative to the DC current. I need to solve for the AC current at 14.7. So don't I just need to multiply that by 14.7, which is my DC current, to give me the AC current? So this is not 14.7. It's whatever current you get over here. Some people put 451.76, and I should have taken more points off on that, because as you can see, it's well below 452, right? It's not at 452. It's, I can't remember what the calculation is, but to actually get this one correct, you would need to have calculated what that current is, which shouldn't be a big deal. It's just a straight line. It's just calculating the slope and finding that point. I will say a lot of people did the AC divided by DC. And how many times did I say it doesn't make sense to calculate an impedance when you're dividing an AC quantity by a DC quantity? I wasn't doing that to be mean. I was just saying it's not a realistic parameter. But for some reason, I know people were confused or felt the time crunch, but the reality of it is a lot of people still did that. And it doesn't make any sense. The whole thing about AC is we're doing things on a steady state time frame. So what you all were saying is, if I do everything in DC, I'm going to take this voltage, which does this, and divide it by this current. What impedance do you get there? This is the voltage and this is the current. You get a time varying current, right? Your impedance would be, you know, sometimes 0 divided by this, and on and on and on. You'd get some random number that was changing with respect to time. So this doesn't work. We can't divide that by that. What we do is we divide our phasor voltage by our phasor current, and then that gives us the value of Z. So that does work when we do that. But these are both phasors. And a phasor is a rotating vector, or it's a sine wave. So both the voltage and the current have to be sinusoidal. Okay? That was the hardest part about this problem, I think, was finding the actual current. But it seemed like, I don't know if anybody actually figured out how to calculate the current. Maybe 1 or 2 of you did. But if you got the 452 or whatever, I think I still give you full credit. For B, which is a saturated reactance, the saturated reactance is, well, I know what this current is here. I've got that value. And I've got this value. So my saturated value was going to be equal to 480 over the square root of 3 divided by my current there, which is 452. And if you put for your unsaturated, if you would have put 601 over here, that even is a harder answer because you can see at 601, I needed a field current of 21.3 amps, which means I'm really saturated out there. I'm way away from the air gap line. So that impedance is not going to be anywhere close to the value that I need. Okay. And then the last part, so this was A, B, and C, which is my short circuit ratio. If you remember the definition, it's the field current at rated voltage and the field current at rated current. So you could have calculated how to get the 601, but that would have been the rated current. So all you needed to do was 16 divided by 21.3. Okay. Questions? This was definitely new material. But my concern is that so many of you still did the AC voltage divided by DC current. What that leads me to believe is that you don't fully understand like where that DC current is going. And I know we just had a lab yesterday, and unfortunately, because of all the having Monday lab and we missed 2 Mondays, we're a little bit behind on labs, but hopefully you're starting to see this DC current goes into this winding that rotates around. It has nothing to do with the AC output. If you remember from lab, we didn't even connect the AC. Remember that AC on our power supplies? Those were all just floating. They never got used. We just used the DC. We did connect the AC to measure voltages, but that was just connecting a multimeter to it. We didn't actually put anything in there. It was literally just a measure. Any questions on number 3? All right, we'll keep going. Number 4. So motor rotational speed is 3,600 RPM, which is another way to say 3,600 revolutions per minute. Go ahead and calculate what that is in radians per second. 1 minute and 60 seconds. How many revolutions? Or how many radians in a revolution? What's that? 2 pi radians in a revolution. So you really only had to multiply by pi over 30 to do the conversion. And then the next part is if the motor is connected to a 50 hertz system, what would be the new rotational speed? So this is part A. So for part B, what you needed to do is you needed to figure out, okay, if it's operating at 60 hertz and I get 3,600 RPM, you know that my mechanical speed or synchronous speed is equal to your frequency times 120 divided by the number of poles. That allowed you to calculate P as your frequency times 120 divided by your speed of operation. This is a 2-pole machine. Once you know it's a 2-pole machine, you can use that same equation for 50 hertz. This was equal to 2. You plug in 50 over here, and then you would be able to calculate what the rotational speed is in RPM. Okay? So you would have needed to go back in that one step and solve for that for part B or part A. Any questions on number 4? Yes, sir. Say it again. N sub n, this is the rotational speed in RPM. Yeah, problem number 1 says the motor rotational speed is 3,600 RPM. Determine the angular velocity. And like we said in this class, we're assuming everything is operated at 60 hertz unless we're told otherwise. 377. Part A or part B? 3,000. Any other questions on number 4? All right, number 5. I just did a 2-pole or 2-phase machine, I should say, to hopefully make it easy. And what we said is the first thing you do, take your fingers, point in the direction, your fingers wrap in the winding, and your thumb points in the direction. So the magnetic field, because of current flowing there, is here, right? Wrap your fingers, point that way. Over here, point into B, wrap my fingers around, point down towards A. So this is B sub B. So all I know is that BA, I'm not sure why that got weird. So my BA, we know is going to be equal to some magnitude of B, and I determined that from the current, and the angle is 0 degrees. B sub B is equal to some magnitude at an angle of minus 90. Now, the next thing I need to know is how do I calculate what these are going to be because of current flow. So my current for phase A, IA of t, is 10 sine of omega t plus 180, and I sub B is 10 sine of omega t. And then I said the currents have been rotated by 90 degrees. So what that means is that omega t is 90 degrees. So all you needed to do was 10 sine of 270. And this is 10 sine of 90. What's 10 sine of 270 equal to? Negative 10. What's 10 sine of 90 equal to? Positive 10. So now the only other thing is it said, determine the net magnetic flux density given the following currents, and the peak magnetic flux is 5 times the peak current. So all you needed to do, your B currents were just equal to 5 times whatever current you had going through there. So this is going to be equal to get to the B, that's minus 10 times 5. And that's positive 10 times 5. So you had minus 50 and 50. So now to get the net magnetic field, B net is equal to BA plus B sub B, which is equal to my A was minus 50 at an angle of 0 plus positive 50 at an angle of minus 90. You can enter that in your calculator, or you can just do this vectorially. Minus 50 at an angle of 0 is the same way as saying positive 50 at 180. So that vector is here. This is B sub A. And then B sub B is minus 90 over here, right? When I add them together, this is B sub B, and then the net is over here, adding them vectorially. So what I can see very quickly is it's the square root of 2 times 50, and the angle is minus 135. because they have the exact same magnet, the exact same magnitude. So you know it's at a 45-degree angle, and you get the square root of 2. So I didn't even need my calculator on this problem. You could have just done it with adding vectors. Some people, they try to add another vector. So some people try to do this. What is that coming from? Should be a magnetic field, right? If you're showing a magnetic field drawing. So where does that magnetic field come from? What current flow causes that? That's a question, because I don't know. I don't know where that comes from. I'm asking you all. Do you know where it comes from? I don't. And so that's not to mock you. It's more like, think about, where does this magnetic field come from? If you can't find it, if there's no wire with a current flow through it, then it can't be there. You can't just assume that, oh, because it's a 3-phase system, I have to have this. This wasn't even a 3-phase. This was a 2-phase system. And that's number 5. Questions on number 5, or any questions in the test? I think the average was a 66 or something like that. I will say there were a lot of grades in the 90s, some hundreds, and then there were a lot of low grades. So I don't know why. Usually you like to have a curve, like the curve kind of did this. So if you looked at the performance, you had, 1 or 2 hundreds, then you had one of these, and then it kind of dropped off pretty quickly, and then it went back up, and then kind of flattened out like that. So I'm not sure why usually there's more people in the middle, and I'm not sure why the people who did in this region struggled as much as they did. I don't know if the material is too confusing. I mean, it's all the same stuff. We just keep applying new material. So what I mean by that is it's still power factors, power triangle, 3-phase power calculations, all that stuff that we've been doing for the entire semester, but now we just apply it with a synchronous machine. That's why we introduced the equivalent circuit model for a synchronous machine, is to be able to help us calculate these parameters. That's all what electrical engineers who do calculations do. They just come up with equivalent circuits. So for tips on improving your performance, I'm not exactly sure, because usually with scores that low, there's just a general fundamental misunderstanding of the material. And that usually means you got to go back in time and look like what was missing. What did I not understand? And dividing the AC current by the DC current, that might be just your circuit analysis. You may not have been taught enough AC circuit analysis to say, you can do this or you can't do this. But when you start to peel back the onion a little bit and say, what's going on? Hopefully it makes sense to you and say, well, I can't divide an AC current by a DC current, because if I look at this right here, that doesn't make a lot of sense. I can't get something like that. You can divide DC by DC because, yeah, I've got a current here and I got a voltage. This is constant, right? I can deal with that as long as they're constants. That's why you can divide by a resistance. But in DC circuit analysis, if you're dealing with things from a transience perspective, you can't even come up with an impedance. Anybody here in ECE or whatever, when you did circuit analysis, what did you do? CdVdt, LdIdt, you got to take derivatives. That's not a fixed resistance. That's an actual derivative. So if something's changing, you can include that. That would mean that your impedance changes. So introducing steady state stuff for us allows us to take that changing part out of it, so we can calculate impedances. So both parameters have to be AC. Just because we take the time changing part of it out, we simplify it. We just take a snapshot in time. It's still there. We just snapshot it. So we look at it at just one specific interval. That's why it's always a phasor, a magnitude at an angle, because we look back at that at the same point 360 degrees later. But with DC, that's not, we're not getting the same conditions there. All right. Any thoughts or suggestions from you? Was time an issue? It seemed like most people had plenty of time. Do you want to do the next exam during class or during lab? I rather give you guys extra time during lab, and it seems like the grades were better during lab, but from what I could tell from the test, at least the test taking time, everybody had sufficient time. But I don't know if people would have taken more time, would have thought about it differently. I mean, we don't have to decide now, but just for you to reflect on and give me advice as to how to proceed, that would be helpful.
I would like to add one request.
Sure.
Can we go further into detail with equations, more equations that come up?
What do you mean?
Lab 3, so, or the fourth technique, but, for instance, going more over the math of the equations.
I mean, how they're derived?
How to use the equations, more into how to use them. That
Okay.
way, we're more prepared on the next step, and I think that was my biggest issue, especially with the mechanical or the magnetic stuff. Being a newer concept, not knowing exactly how to use those might have.
The magnetic equations?
Yeah,
Okay.
I was pretty confident in the test before I came in. Night for grinding, the entire, set of weeds, right, but, I feel like it was because I thought I was using them the right way, but I didn't look. So I think that would be,
Sure.
beneficial as well.
Well, what do you think over here, when I presented it this way, if you can share your own personal experience, what was the misunderstanding between what we present here versus when you walked into the test? And what were we thinking?
Here, so for number 5, for instance, right, calculating BA and BB, right? I did it in completely different ways because I had completely different notes from looking back at slides and writing them down on this paper, looking at videos and whatnot. I used the method of just replacing B with I, that's how I understood it. Not the calculate what B will be from I, and B has its own vector to it.
Okay,
So I'd say going more in depth with the, mathematics of it, being able to go through the entirety of that.
Sure.
That would be very beneficial. I think that thought about the majority of the.
yeah,
That's what you're doing, like, I feel like you need more examples in class, and, I have followed on the side of that, like, I don't have any intuition from like prior experience with, examples in class, you go, okay, this scenario, I can't do this, I can do this, like, shifting the vision on the computer, and comparison the situation, and I feel like, let's say, you have the equations on, like, you understand the variables, from. When it comes to like, doing the instance of how she, if this verification or any information back up to. Which ones are slightly outside of the equation for that, like, shift the equation around, like the efficiency one, simply for that. Or the full one, for efficiency, or how should that, the different, it's,
okay,
more. Critically outgoing.
yeah. Well, the only thing I would say about the magnetic field one is that was the one we did the pole swapping. Remember that take home problem where you get to swap the problems around? But maybe it was confusing because I did the MATLAB stuff. Remember I had said, let's switch the currents around, and then we did that in class. So we did a lot of them, but maybe it was included in the MATLAB calculations, but that was what was confusing. What's that? Yeah. Well, yeah, so the only reason why I do MATLAB is, again, it's a calculator. I just show you the calculating results. I don't do that to make you better at MATLAB. It's just like, here's the results and we calculate it and it matches what we do. I don't do that to say, you need to do this. I do this just to hopefully so that I can do the calculation like, oh yeah, I see it. And it's very logical. Here's how we got BA, on and on and on. And it kind of walks you through the process. So hopefully it summarizes it. That's why I like to do the MATLAB stuff. But we have to do the background stuff, which is on the paper and pencil. So maybe the providing the two together is confusing. I don't know. Okay. Thanks for the suggestions. Any other thoughts or suggestions? Are you satisfied, dissatisfied, or? Do you feel like you prepared enough, or was having a test after break not a good?
It's definitely better to have it Thursday.
Yeah.
Having that review session Tuesday, being able to kind of talk about it again, it's good.
Okay,
I know I was pretty tired Monday morning. So it would have been a tough time to take that again.
so it sounds like maybe I should do a review session on the Saturday of break, right? So we'll come in and make it mandatory, and everybody will be with no whatever's in their systems or all that stuff. As I mentioned, I was forbidden from going anyplace fun on my break, so I just worked, which is fine. But yeah, we can adjust it. We could have done it before break, but I got the feeling if we had done it the week before break, it would have been even worse outcome. Because people were already on their trips, right? But yeah, this is just the hard part about how the university sets things up. If we didn't have that rule about you couldn't have exams during the last week of classes, it really kind of really forces you into this little really tight window. The only other option would be to go to 2 exams. Would you rather do that? A lot of money invested. You get a lot on the line if there's only 2 exams, right? So you could mess up a test and it's no big deal. But 3 exams, if you mess it up when it's 2 exams, now you're talking 20-something% of your grade. Changes the calculus a little bit. Okay, anything else? Remember, if you also need practice too, the Shomes Outline series are really good. They have a lot of stuff. And feel free to come see me. This is when you, as an individual, it's better to wrestle with the material. So just be careful about if I do equation after equation or problem after problem, it looks like over here, oh, I see how to do number 5 perfectly fine. Well, go out and have lunch and then come back and show me if you can do it in 5 minutes or 30 minutes. And I'm not doing that to be mean. The difference is like, this is in short-term memory. I see what you did, but to do it in long-term memory, to actually have it make sense, that's the wrestling with it. So that's when you get to go back and spend the time, and then your brain, that's the learning process. You have to wrestle with material. That's what I need to do. So I have to think about it, come back to it. And so somehow coming up with a time and that experience to be able to do that is really helpful. That's why study groups are really good, because some of us need motivation. I know I do. So how do you motivate? Well, if you're really good, you just do it on your own. But if you need help, you have study groups. Because if 3 of you are in a study group, hey, let's study for this next exam together, and we're going to pick a 4-hour block to study. You show up and you're not super motivated, but hopefully your study partners will be, yeah, we got to focus on this, and that gets you more motivated. So you can get external motivation that really helps you. Well, helps me. But you're all 3rd year, most likely 3rd year and greater students. So, you know, a lot of this stuff, hopefully you've figured out what works effectively for you. Never too late to teach an old dog new tricks. Okay, well, if there's nothing else, I will see you all on Thursday. We'll continue induction machines. Have a great day, everyone.